Thank you, guys. Thank you very much for a great introduction. Good afternoon, everybody. I think you guys are enjoying or been enjoying the sessions for the past couple of days. I personally enjoyed a lot today. I was there part of three to four sessions. Extremely good, and thanks for the organizers for giving me an opportunity to talk to you about the things, what we wanted to share, or what we're doing in Mercedes-Benz at the moment. Originally, we planned to have two speakers. Unfortunately, the co-speaker, Sabina, had to pull out in the last minute because of illness. But nevertheless, we can take it forward, and I would be talking about the data science part of it as well. So probably we'll get started. Before I start, I have a few questions to understand the audience. How many of you in this group feel there's too much of data in the monitoring at the moment, and it finding very difficult to come to a conclusion if there is a problem? Okay, it's a handful of them. And how many of them have actually implemented some kind of AI or data science to correlate different dimensions of data to get a suitable solution for this? Okay. I hope I'll probably give some more information on our journey, how we achieved this. And I think this should probably help you guys achieve something of similar sort. There is no specific way to achieve this, but depending on the use cases, depending on the infrastructure, if it's a cloud, on-prem, or different applications, middleware, and so on and so forth, there are different ways to achieve this. So as part of my talk, I'll be talking about the observability and pain points. I hope observability itself is clear for most of the people. It's different kind of data sources. It's logs or metrics or traces and so on and so forth. I would be then touching about the infrastructure pain points itself. What is exactly the pain point? What drives me use AI? The third one, which I would be talking about, is how can we think about solving pain points? Or what are the things which we can try to solve with the data itself? Because like I mentioned, there's so much of data around. There are so many infrastructure data. And we sometimes feel 50 or 60% of the data are redundant. We don't need them. As long as we don't get an alert, we don't think about using them. So that's the reality. But the other way of looking at this, how can I implement some kind of a proactive monitoring? I need these data. The 60% redundant data, what we think it's of no use, this is what brings a lot of value. There is a data science behind it. It's not something which we can directly implement. I would not call it predominantly everything is AI, but I would call it data science. There is a data science involved in it, and we can think about using this particular data science to predict it. Towards the end, I will also give a reference architecture with all the technology what we have in place to build this kind of observability solution. So let's get started. So like I mentioned, the observability system is more of metrics, logs, and trace. Prior to the observability, I would say 3 or 4 years back, we had log analytics separately handled, the elastic stack for this, and ELK, and things like that. For metrics, there were several different tools which are used. Sometimes relational databases were used to store them, and traces, typically AppDynamics or something like that. When I look at the different components, there are databases which we monitor. We have infrastructural component, firewalls, and so on and so forth. We need to consider these information, and middleware components. There are Kubernetes, for example. This forms a huge container platform these days, either on-prem or on cloud. And there are other middleware tiers which we need to consider to get this information. That's a lot of data. That's pretty much millions of metrics per minute. In infrastructure like in Mercedes, where we're talking about more than 30,000, 40,000 servers per region, we're talking about millions of data. And like every person, I think I also was listening to a couple of sessions where we spoke about we don't really worry as long as this alert comes up. We look at our mobile phones, our pagers, our SMS alerts. We react only when something happens. Yeah? And the dependency between the logs, traces, and metrics are often forgotten. There are systems. Grafana has done a wonderful job to bring up Locky, the metrics from different data sources, and tracing together, but we don't often bring all these information together to find the value out of it. The biggest question which comes to my mind is this one: can the operation team generate value, or can they actually find all the information together and in one shot say, okay, the system is performing well or not performing well? Or are they in a position to do the complete job, or the point to say the system is going to crash in the next 2 months? There are several ways to look at it, but we had a huge challenge in front of us to do this, and every time we were too, I would say, reactive. When the system really crashed or something really was not responding, we had to think about how to do this. So that is something which we tried to resolve in the past couple of years at Mercedes, and this is something which I'm going to touch upon today. I thought it's easier for me to take one specific case and take this journey together. So one specific focus area is the cloud databases itself. There's been a lot of talk about moving the databases or the data, I would say, object stores to the cloud, or use of various offerings from different cloud providers. And they promise managed data sources. So they do take care of managing the databases, and we don't have to worry about everything. But I still see two areas in this. One is the managed part. What is really managed? Patch management, of course, it's managed. Availability of the databases itself is taken care of. Scalability. So this is basically an overview of it. They say these are the three things which are managed. They can scale, and the availability is ensured. SLAs are defined. Of course, there are certain areas where also they speak about SLIs and SLOs, depending on the SREs things. But the unmanaged or the pain points, what we were facing is what to scale. So if I have a problem on the memory level on a database, or if I have a problem on the CPU level, is it really the CPU and the memory which needs to be scaled? Or is it something else? Is this some kind of a tuning in the database itself which needs to be done? I think this applies to the middleware components as well. It's not just for the databases, and also in the infrastructure. The next point is, should I optimize something? Should I do, perhaps partition them? Perhaps I split the application into smaller microservices on the Kubernetes front, or try to do some kind of optimization so that I don't have to, purchase so much of resources on the cloud. The last one is the database really self-healing. Can it heal on its own? Even though they say it scales, it is available, self-healing is completely a different topic altogether. So it's more of a proactive approach we need to follow to achieve this unmanaged part. And this comes from the monitoring itself. It comes from the logs. It comes from the traces. It comes from the metrics, which has been put across, which has been ignored most of the cases. And these are the areas we need to probably think about looking at getting more values out of it. So let's probably see one of the problems. And this is something which most of us really think about every day. When I look at, this is a classical Grafana dashboard, where I have some CPU metrics in them. I see a peak. Probably it's a little small, but I can read it out. It's 38% CPU. So when I look in front of this dashboard, what do I think about? Is it a problem? Is the behavior normal? There is a peak. It's normally at 1 or 2%, but all of a sudden it gets into 38 or 39%. Is it a problem? For me, at the first look, is that I still have 60%. I don't have to worry about it. But this particular peak might tell me something. It is not telling me exactly what it is, but it is trying to tell me there is some kind of behavior change. But I'm not able to conclude it. So what did I do next was start looking at the data, trying to see, okay, how can I progress with this? The first thing what I did is I started to compare the last 3 days with today. Okay, this is how it looks. It's so messy, and it gets so disturbing. But, well, for me, it looks normal. I mean, it's still not a problem because when I compare it in the last 3 days, it still looks normal to me. I say, okay, it's still normal. Then I start thinking about, okay, last 3 days, probably the application was not being used anywhere, or the database itself was not being used. So let me compare the previous week, the last couple of weeks, on the same day. Okay, let me give you another thing. Last couple of weeks, on the same day, similar workload, not a holiday, or a similar kind of a day, busy day, how is it looking? It still looks okay, better than the last 3 days, last couple of weeks. I mean, it looks okay, but I'm still not able to conclude. The point what I'm trying to make is, if there was any kind of point here, if there is any kind of discrepancies or change in the behavior, we would not see this. We would absolutely ignore it, and we will go forward. And this is what we call it as reactive monitoring. We compare the last 3 days. I've seen systems where they don't even compare the last 3 days or the last couple of weeks. They only look at the today status quo, and they go forward with it. So what I really want to see is this red dots, very clearly these red dots. I don't want to see anything. I don't want to see too many graphs here. And the operations team precisely want to see where these red dots are. And this is where they can start working on, okay, it's 38 to 40%. I have purchased 100% CPU. There is absolutely no problem with it. But I still see red dots on it, which is alarming. This is proactivity. So after maybe a couple of weeks, this peak might periodically increase over time, and it could stop the system. This is what we can think about finding an anomaly. This is, for me, an anomaly detection. Yeah. So moving on, what are the different points we can look at? I think one of the areas which I already spoke about, anomaly detection. What we are also thinking about is the deep insights. So there are data coming from logs. Let's say in a typical database system, there could be some kind of signal which is being sent from the database product itself. There could be signal which is being sent from application. And also, there could be signals which is sent from traces. So these 3 areas where we can combine and get some kind of a deep insight, get a correlation of these values. I have brought in a very interesting part. The database itself is 8 terabytes, as you can see. And the customer keeps complaining, or the end user keeps complaining, the database is slowly coming to the 90% usage. And we will have to, take a look at how to, increase the storage and so on and so forth. Of course, the storage is not that expensive, but still, when we think about having a 10 terabyte of storage, we need to back up them on an object store, or back them up on a tapes, and we need to restore them, maintain them. It's going to be a cumbersome job. So what we started to do is get some detailed information on it. What exactly is being used? What is being allocated? Is the behavior normal, or whatever it is? And what we found is it's close to 5.4 terabytes from this 8.5 terabytes. Were vacuum. They've been deleted, or they've been moved, or they've been allocated, but never used. So these are the information. Most of the time, we actually ignore them. End of the day, it costs a lot of resources, because this is, say, for example, in a normal terminology, when I do a select on a table on such a big database, and one of the tables is like 1 or 2 terabytes, the cost of this particular SQL statement running into the entire 1 terabyte storage is going to be huge. It's going to scan through all this 1 terabyte. It's going to consume CPU. It's going to pull up the memory. And the entire system is going to be busy. So when I remove these unused pages, I try to find where this unnecessary vacuum is, it's going to free up a lot of resources. This is going to bring us a lot of return on investment, especially on the cloud. Because on the cloud, when I provision a database, it's going to be a couple of clicks. I'm going to say, I need this database, or I need this resource. I'm not going to optimize this parameter the way I want it. We need a system. We need a monitoring system to actually look at what parameter is wrong for this workload. We don't have a default workload or default database for all. There is nothing called default. It should be tailor-made for the workload. So that is when we started to build some kind of a system. So I've spoken about a little bit of the pain points and what are the potential areas where we can look at. Now, probably looking at a little data science perspective on it. How do we start looking at it, or what is the procedure we need to build it? So, I think for the folks who've been using machine learning, for the folks who've been in the data science, this should probably look very familiar. The approach what we used, we started with a lot of tools. We started with enterprise tools, or we started with TensorFlow, tailor-made, or the things which are already prepared for more than a year, and we were not able to get the results what we wanted to. So we used this open source approach to use Python and the libraries which are embedded in Python, which helped us solve a lot of problems. The procedure, what we followed for prediction, is very simple. We build or train the model on a monthly basis. When I speak about training a model, it could be a single variable or multivariable, a combination of both. So when I speak about I need a model, so let's say I think I showed you the curve of the database and things like that, CPU. And with this single curve, it's very difficult to understand with 1 day or 2 days workload. And what we did is we combined them as a model and stored it separately on a monthly basis. The second one is, on a daily basis, we used the current data against the model and forecast to see what's going to happen tomorrow. It's not 100% one-to-one. I would come to that point on how do we achieve the accuracy, or how do we measure the scores. That's the second part. But what we saw is the graph on what we can see on the slide. Initially, we can see the orange graph. It was like closely matching to what it really works. And over a period of time, as and when it learns with the data and the different things, like if it's on holiday, workload factors, we have to constantly give the factors as input, and we started to get a lot of results in it. We could see that this is going to happen this way based on the data, and if the model does not match the current data, it's clearly an anomaly for us. So there is something which is going wrong on the system on a general scale, and this causes a lot of problems. This could cause a lot of problems. And how do we, a little bit on the data science front, forget about this. This is the complicated decision tree, or the tree it looks like for us for one model. It's pretty complicated. Just wanted to show how the model actually looks. But what we wanted to use is a classical decision tree. So decision tree is to say, how do I classify my data? Is the data being classified on the positive side or the negative side? I keep classifying. There are several algorithms, Python-based open source algorithms, which could be used. And what we use in practice, or what we try to use, is two things. One is the XGBoost. It's called extreme gradient boosting. There are a lot of articles on the internet. You can take a look at it. And Python libraries are also available. And the next one is the recurrent neural network. In fact, we have a lot of use cases on the recurrent neural network. These two comes under supervised learning. So predominantly to identify how, in simple terms, a recurrent neural network is something like a person X is allergic to fruits or fructose, and he doesn't eat apple or something like that. So the recurrent neural network is something, it tries to get the data from the previous train. So this person does not like, he is absolutely allergic to fruits. This particular neural network ignores the combination of he or she or whatever in the context, because this context is irrelevant. It takes this allergic to fruit as the parameter, feeds into the next layer. We could call it as hidden layer or an output layer. And this output layer takes this allergic condition to the next. So It's basically used for time series analytics or natural language processing and something like that, and we got a very good result in it. But the next part, with regards to the neural networks or the recurrent neural networks, it was resource intensive. And when we started, it was OK, but with huge amount of data points, it consumes a lot of CPU. We were not able to handle it. And that is when the gradient boosting came into picture. And I would recommend to use the gradient boosting. Of course, we would not get the accuracy from what we got from the neural network. You can see we normally measure the accuracy with R square. This is the terminology that we normally use for data science. And this particular XGBoost was not that productive, or it was not giving the result what we were expecting. So irrespective of that, for trend analysis, if you don't need 100% accuracy, for trend analysis and things like that, XGBoost was really good. We didn't need to use GPU. CPU was more than enough. And we were able to get the predictions in line, and we were able to get the anomaly detections. So looking at the time, I think I'll have to push quickly. This is one of the areas what we wanted to see. Like I said, to achieve one single metric, we need to get a correlation of various patterns. And it matches each of these metrics, and these red dots gives an indication this is where it is going wrong. And it correlates together and gets us a point to say, OK, tune this particular parameter. This parameter is not, it gives us a recommendation to say, this parameter is going something wrong. You don't have to increase the CPU or memory. Please optimize this parameter. Don't get into the details of it. And so that you don't have to go on purchasing a lot of resources on the cloud. Yeah. Now, quickly, in the last 5 minutes, I would probably touch upon the ecosystem itself. I think that's more important. We spoke about our pain points. We spoke about the data science part of it. How did we realize doing this? I mean, it looks like, or it sounds like a very complicated environment. And we started to work on something like this. So like I mentioned, I was very specific in this use case for Postgres on an AWS environment. We used a data collector. There are several data collectors you could use. You can use CollectD or whatever. We use Telegraf. It's a Go-based data collector. And we pushed into a time series database. It's TimescaleDB. It's scalable, and it's also open source. What we used for building the model, or the Python model, what we wanted to use, we used Airflow. This is the data orchestrator. It builds or creates a directed acyclic graph and builds the model and stores it in a. You can use a normal version controlling system to store the model. And this particular product, or this data orchestration tool, open source orchestration tool, helped us do a lot of things like comparing the model, forecasting the model, and so on and so forth. And then push the data to data visualization. We initially used Grafana, but we thought, getting the granularity of all this information, we needed a Python-based framework. So that is when Streamlit comes into picture. Streamlit is a data visualization package for Python, and we use Streamlit for this. And you can actually get the granularity. Not just the granularity, you can also scale it. You can actually scale it on several components. You can use a caching layer. You can build a caching layer on this so that for big data analytics, or when we are talking about millions of data from the complete infrastructure, this would do a lot of good things. So looking at the time, I think I still have a couple of minutes to touch upon this. I think probably one of the things what I also want to talk about, the entire infrastructure what we built was on a Kubernetes platform. So you can activate an autoscaler. It scales based on the information. And we were able to get the information or the predictions on a real-time basis being pushed into the data source. And it's helping a lot of customers. It's helping a lot of projects to foresee problems. Yeah, like I also mentioned, our main aim was to reduce too much of investment on the cloud, because on a cloud data source or any kind of infrastructure in the cloud, if you don't manage it in the right way, it would explode. We would get an exploding bill, and this should be avoided. And the way we found was to use some kind of prediction like this. That's pretty much from my side. Any questions?
So first of all, thank you, Satish. Do we have questions in the audience?
Thank you very much.
Yes.
Have you done that for every cloud instance, every VM you have running?
That's the plan. At the moment, not for everyone, but that's the plan, because potentially we see a lot of resources being wasted everywhere.
Thank you.
Yep.
Do you have some retention period for the database, Timeseries database?
Yeah. For the preparation of the model, we use a standard 3 months data, because that is what actually gives us a lot of good result, because we started with 1 or a couple of weeks, but you see the seasonality. The seasonality of the data varies from 3 months to 3 months. And for infrastructure, I think 3 months is a very good period. Yep.
Yeah, thanks for the talk. It was very insightful. These anomalies you get out of the system, how do you act upon them? Because is every anomaly really a problem?
No. An anomaly is not a problem. It's an indicator. Like I mentioned, reactiveness is when the system completely stops. Yeah. So anomaly is an indicator to be more proactive, to say there is something going wrong in it. And initially, as we started with a normal anomaly, it was not giving us any kind of indicator. But over a period of time, as and when we build the complete workflow, when this is going wrong, check this. When this is going wrong, check this. And not just in the current real-time data, but a 3 months model. So compare this, how it was, what is it supposed to be? And this gives an indication to say, try to optimize it. Otherwise, you will either ending up investing a lot of resources on the cloud, or you would probably end up crashing the system.
Do I understand correctly that you more use the anomalies to assist you in finding where it could be, where the actual problem is?
Absolutely.
Yep. Okay, thanks.
Okay, thank you, Satish.
Probably a last slide. If somebody is looking for something, this is something which I brought from the company itself. You can scan the QR code. Thank you, guys. Thank you very much.